Good morning, everyone. I would like to thank el Congreso Internacional de Innovación Docente en Educación Superior for the opportunity of presenting my paper. I would like to thank my team and especially our coordinator, Gaston Sanglier Contreras, for the opportunity. Today, I will present a paper titled For Environmental Data to Learning Ecologies: How Classroom Context Shapes Attention and Cognitive Fatigue in Higher Education. This research is part of a broader project that connects architecture, environmental psychology, and educational ergonomics. In particular, it focuses on how the classroom context influences sustained attention and fatigue among university students, with a case study in architecture education. Student performance depends on many factors. We usually talk about abilities, motivation, or study strategies, but we rarely consider the influence of physical environment. Think about a typical classroom: temperature, humidity, air quality, noise, lighting, and even how desks are arranged. Each of these factors has a direct impact on how much students can focus, how tired they become, and how motivated they remain. Architecture students, in particular, represent an ideal group to study. Their workshops last for several hours. They must combine creativity with technical precision, and they often work under tight deadlines. This makes them especially vulnerable to the contextual discomfort. Previous studies have already shown clear links between environment and learning. For example, offices with poor air quality report decreased concentrations, and schools located in noisy urban areas often see reduced comprehension. Yet, universities often ignore these variables in their teaching strategies or classroom design. This creates a gap. On the one hand, we know the context matters, but on the other hand, it is rarely integrated into pedagogical planning. Our work tries to close the gap. Our study builds on three perspectives. First, Bronfenbrenner's ecological theory and the idea of the learning ecologies. Learning is never isolated. It happens in a system where students interact with people, tools, and their environment. Second, environmental psychology. Research shows that high CO2 levels reduce sustained attention, that poor thermal comfort increases fatigue, and that noise above 55 decibels lowers comprehension and productivity. Imagine trying to design a complex project while exposed to constant background noise. After 1 hour, the brain is simply less efficient. Third, educational ergonomics. This field focuses on how classroom design, layout, ventilation, furniture can support or limit student performance. When students feel physically comfortable, they regulate their effort better and stay engaged for longer. Our study combines these perspectives. The aim is not just to describe environmental factors, but to connect them with concrete evidence of how students perform in real tasks. Based on this framework, we established four objectives. First, to measure how temperature, humidity, and noise influence sustained attention, motivation, and fatigue. Second, to create a contextual comfort index that integrates both objective environmental data and subjective student perceptions. Third, to link these conditions with functional performance, using productivity measures and quality rubrics. And finally, to provide guidelines for a classroom design and teaching strategies based on these measurable thresholds. In short, we want to move from raw environmental data to practical recommendations for higher education. We designed a case study with architecture and interior design students at CEU San Pablo University in Spain. The context is important. Students work in long 4-hour workshops with intense cognitive load and a strong need for both concentration and collaboration. Data collection started with 3 sessions and will continue until November. We use two main instruments: a Netatmo weather station that records temperature, humidity, and CO2 levels with both indoor and outdoor modules, a wall-mounted sound level meter capable of measuring from 30 to 130 decibels continuously. Environmental data was recorded every 5 minutes in CSV format. This provided a precise log of conditions across the entire class. At the same time, students completed short Likert scale surveys on attention, fatigue, motivation, and perceptions of comfort. We also observed their time on task, interruptions, and collaborative behaviors. Finally, we evaluated their work through productivity counts and quality rubrics. A key methodological point is alignment. Environmental logs were synchronized with surveys, responses, and teaching blocks. This allowed us to directly connect specific conditions, for example, spike in CO2 or noise, with moments of lower attention and higher fatigue. What does the data tell us? Context matters, and it matters in a measurable way. When temperature, humidity, or noise levels cross certain thresholds, students lose focus, produce less work, and report higher levels of fatigue. This is not only a subjective perception, it appears consistently across environmental records, surveys, and performance measures. For architecture students, this is particularly critical. Their projects require sustained technical precision and teamwork. Small variations in comfort, just a few degrees above thermal neutrality, or 10 decibels more of background noise, can drastically affect their efficiency. Fortunately, monitoring tools are now affordable and precise. With weather stations and sound meters, universities can gather continuous data at a low cost. But data alone are not enough. The challenge is to translate them into action. For example, if temperature rises above 26 degrees Celsius, ventilation or a brake should be introduced. If, noises, if noise surpasses 65 decibels, groups may need to be rearranged or activities adapted. If surveys show a sharp rise in fatigue halfway through the session, workload can be adjusted or a change of task can be introduced. These are simple, concrete actions that turn environmental awareness into pedagogical strategies. They represent the step from passive measurement to active improvement. The conclusion is clear. Classroom context matters. Temperature, humidity, air quality, and noise influence attention, motivation, and fatigue. Measuring these variables with simple tools provides actionable data. When combined with student perceptions, they form a contextual comfort index that links environment with performance. For architecture students, optimal conditions support not only technical precision, but also collaboration and creativity. For universities, integrating environmental monitoring into teaching practice is a way to improve focus, reduce fatigue, and maintain motivation. Ultimately, this study lays the foundations for a broader research program. Future sessions will validate thresholds, refine the comfort index, and expand recommendations for higher education learning practices. The message I would like to leave you with is simple. Classrooms are not a neutral container of learning. They are active agents that shape how students think, focus, and create. The space teaches. Thank you very much.